And there are some downsides to using 16S analysis. There are some biases that you might find, but we can discuss that later. And then also I wanted to classify the bacteria based on phylogenetic analysis, to get more of an idea of what they are and what they are doing. So the methods that I've used, I had a select sample of 5 hylochrysosceles, and they happened to be all adult males. I did not choose to have all adult males. They were just easier to find out in the wooded areas. And they were collected from a single collection site on a single line. So these 5 frogs were brought into the lab, and I euthanized them in a carbon dioxide enriched solution. They just knocked them out, and then I took this picture of them. And after I took that picture, one of them started to twitch, and put it back in the freezer before they woke back up. And then I put it into the freezer to finish the whole euthanation process. I then dissected out their intestinal tracts, and I dissected from the stomach all the way down to the end of the intestines. And then I homogenized those digestive tracts separately in a PBS solution with ceramic means by vortexing it for 5 minutes. It was completely homogenized. After homogenization, I extracted DNA from a pooled sample of those gastrointestinal tracts. After DNA extraction, I ran a PCR using 16S bacterial primers that are very specific for the 16S RNA. And my conditions for PCR consisted of 20 cycles at 55 degrees in needle. And that is a very low cycle, low set cycles from that. You can see in my diagram that I did have amplification in all the samples I ran, here, here. There is a band here. Can't see it. I promise it's there. You can look on my computer. It's much easier to see it. And then there is a band here and here. And it is approximately 1,400 base pairs, which is the approximate size of the 16S RNA gene. So after PCR, I pulled my PCR reactions together and I cloned them, showing you a representative clone from each of those 28 groups, as well as the number of clones within each of those groups. And then after I grouped them, I put them into the GenBank database to find close relatives. So I do have the closest relatives that were associated with each group listed here, as well as the identity to each. And the identities did range from 90%, which is at the bottom, all the way up to 100% identity. So the sequences that were from 90% up to 96%, that shows that they're not the same organism. Like I said, 98% higher is often considered the same percentage. I submitted these sequences to the GenBank database, and they have been accepted for publication. So those last 8. So these pie charts are simply giving you a visualization of my GenBank comparisons and how they can be grouped based on phylogenetic. These strictly are off the GenBank comparisons. And what I want you to notice is that when I grouped my sequences based on these comparisons within the phyla, 46% of my sequences could not be grouped into a phylum, while the remaining 54% could be grouped and further subdivided into specific genera. But I just want you to get from this that 46% could not be grouped based on phylum. So then I ran my phylogenetic analysis, and I did use a bootstrap maximum parsimony at 1,000 replicates. And you'll see that there are values here at the nodes. These values are basically telling you the percentage of times that these organisms grouped with the one closely associated with it. So the higher the number, the better, the more accurate it's considered. So based on my phylogenetic analysis, only one of my sequences could not be grouped into a phylum. I could not confidently group it into a phylum. While the remaining sequences, I felt pretty confident with my groupings. And those phyla included Bacteroides, Proteobacteria, group of Microbia, and Ficus. I further analyzed this data to see how much more specific I could go with their classification scheme. And I felt fairly confident grouping them up to the family level. Now, if you notice within this phylogenetic tree, I do have my HCA samples. Those are my sequences. But then you'll also notice several other sequences included, some of which, like these, do not have asterisks after them, and some of them do have asterisks. The ones that do not have asterisks are those that were closely related to my organisms from the GenBank comparisons. But those that do have asterisks are ones that were not closely related. They're actually distantly related. It kind of gave me a way to better estimate what families my organisms were in. So the results from my phylogenetic analysis, I was able to group all but 2% of my sequences into a phylum. And that 2% was that one single sequence. And then I felt confident in my groupings down to family. And I'll go through each of these. I performed rare factor analysis on my 50 clones based on that phylogenetic family classification to determine whether or not I needed to continue sequencing more clones. Because like I said, I have 150 clones, but I only sequenced 50. And basically with this analysis, what you see is when your curve starts to plateau, that means that any additional data that you were to get, it would not significantly affect the results. In previous studies, and these are based on more culture-dependent studies, and 16SRD analysis is not culture-dependent, it's actually culture-dependent. But based on previous culture-dependent studies, they found that the major bacterial groups found in vertebrate intestines include the Cytomega Flavobacter bacteroides group, or CFB, as well as the Formicodes group. Some minor bacterial groups that they found have been Proteobacteria, lactic acid bacteria, Bifidobacteria, Spirochetes, Verrucomicrobia, Fusobacteria, among many, many others. And I just kind of put down my percentages of each, which I'll go through again in a minute, but just to show you which ones I was able to find within my organism. So starting out with the largest group that I found were my bacteroides that made up 48% of my samples and included the families Bacteroideaceae and Porphyromonaceae. These organisms are primarily anaerobic, obligate anaerobes, and they often produce acetate and succinate, which are utilized within the intestinal tract. And many of these are opportunistic pathogens, but they are found in normal flora of other organisms. And many of the organisms, specifically one that I found, Bacteroides fragilis, many actually metabolize chitin, which we would expect to see in an adult frog. So some of the organisms that were relatives in the GenMate database with the percentage of homology 9 were Bacteroides fragilis, Parabacteroides gorgonia, Bacteroides ovidus, Bacteroides intestinalis, and Bacteroides claris. These are all commonly found in other intestinal tracts. The second largest group that I found were my Formicodes, which made up 32% of my HCA samples. And these included the families Clostridiaceae and Lactospiraceae. These are also usually obligate anaerobes. Many of these actually still to this day remain in culture, so it would be very difficult to find these if you were doing simply culture-dependent techniques. And then many of the organisms within this phyla are butyrate producers. And usually when you find butyrate producers within the intestinal tract of an organism, the organism is healthier. And that is because the colonocytes within the intestines actually prefer to use butyrate as an energy source. So usually there is increased health. So organisms I found within my samples were closely related to Clostridium ramosum, Robinsoniella piorensis, and the Doria species. Now Robinsoniella piorensis, that whole genera was just discovered in the last year, and it was actually discovered in swine sample, swine fecal sample. One of the smaller groups that I found were Proteobacteria, making up about 14% of my sequences. And this included the families Enterobacteriaceae and Aeromonaceae. And many of these organisms do have the ability to metabolize chitin. And actually, many of the organisms, or I won't say it like that, but actually, Proteobacteria, out of all the organisms that I found, this is the only one that includes facultative anaerobes, facultative anaerobes. Everything else is strictly obligate anaerobes. So one organism that was very closely related to one of my sequences was Aeromonas hydrophilia. It had 99% homology to a single sequence in my sample, which is actually, this organism is the causative agent of red leg disease in many reptiles and amphibians. But it's also found as normal flora within the intestinal tract, so it is an opportunistic pathogen. There was a previous study done culture deepening studies that showed out of a sample of about 200 frogs, 46% of the isolates were Aromonas hyperphyllae. Aromonas hyperphyllae does use chitin as a carbon-nitrogen source, and it actually contains all the enzymes required to metabolize chitin. The final small group that I found were the Verrucomicrobia, which included Verrucomicrobiaceae. There were only 2 of my sequences within this group, and both of them had 98% homology with Akkermansia mucinophilia, which is a mucin-degrading organism. They usually use this mucin as a carbon and nitrogen source, and they also use it for energy. And these two are all